Now, like to share OneNote. Okay, please, could you tell me if you can properly see the OneNote file?
Yes.
Okay. So let's start with a first exercise about the displacement method. It is not working. Why is it not working? Sorry guys, just give me 1 second. Okay, now it's been resumed. Now let's see. Oh, okay. Now I can also draw. That's great. So we have this kind of structure. So all the all the dimensions are out. Okay, we have a uniform load acting on both the beams. We have node A, node B, node C, and node D. We can also call the beams beam A, B, and C. This will come in our help in a couple of minutes. So we have two beams and one column under a uniform load acting on the beams. This is very similar to what you've seen before with Professor Gentile. And how can you not hear this echo? Sorry. I hope you have all drawn the exercise. And now we can go on. The point of the displacement method, as Professor Gentile has shown you during the first part of the lecture, is basically that you start with a structure that can be structure determined or undetermined. In this case, it is obviously undetermined because we have a lot of redundancies. But it follows a philosophy which is opposed to the one of the first method. The first method required that we start from a structure that is structure redundant, and then we remove one redundant restraint at a time, and for each redundant restraint we remove, we add a static unknown. And then we impose compatibility equations in order to resume the actual value of the static unknowns. Here now, we work in a completely different way, the opposite way. We start with each node that is not restrained, and we fully restrain it in order to prevent any possible displacement. In this case, the only node we have to focus on is node B, obviously, okay? Because it is the one that can undergo displacement that we want to prevent. As before, we have the possibility to use the superposition principle. And what's the superposition principle aimed to? Basically, in the first method, we wanted to impose compatibility. Now we are providing the nodes with more restraints in order to study the effects of any class of displacements, namely the displacements, vertical displacement, horizontal displacement, and rotations. We study the effect of each unknown displacement in the nodes that we have. In our case, it is node B. And then we impose, we study the effects in terms of moments and forces acting on the node that we are restraining. And we impose equilibrium equation in those nodes so that we can find the actual values of displacement or rotations that ensure equilibrium in those nodes. So, also similarly for the first method, we can use the superposition principle. So in this case, we start with case 0. That is the one where we have only the external load. Okay? No, apologies. Before doing this, I have to understand, I have to declare which are the displacements I want to explicit. Okay? So we said that we work on the node B, we restrain it, blah. So I draw a sorry, I draw a box where before I had node B, meaning that this node cannot rotate. Okay, this is the meaning of this block, of this box. Then, do I have to impose that that node may have a transversal displacement? No, because we are assuming that the beams A and the beam B are rigid, are axially rigid. Okay, so we say that the axial rigidity, the axial stiffness, goes to infinity for beam A and B. So since the displacement in at least one node in the beams A and B, in this case both node A and both node C, we have hinges, we know that we cannot have any lateral displacement. It means that no node in the beam A and B can have horizontal displacement. Because it means, if we add, it means that each of them columns are either expanding or contracting. But it is impossible for this condition. So we cannot have any lateral displacement. And what about vertical displacement? Well, it is prevented as well because the axial rigidity is true also for node B, node C. Okay, so the only displacement that, in principle, I may have is the rotation in the node B. Is it clear? Yes, no?
please.
Well, I assume
The last
that it
part.
is clear. So, no. So we have to study the effect of the load Q and the rotation phi in the equilibrium in the node B. Specifically, the rotation equilibrium. The rotation equilibrium because we are preventing the rotation in the node B. Okay? So we just study the effect of a generic rotation phi. Now, superposition principle, case 0, where we have Q acting and phi is equal to 0. So we fix the rotation equal to 0, and then we study the effect. Now, it is better to explode this structure. So I have just put a cut. I just cut the beam A, B, and C in correspondence of their conjunction with the node B. Okay? Why did I do that? Because I want to explicit what Professor Gentile has already told you in the first part of the lecture, that flexibility coefficient can be applied or on the node or on the structure, but they are always the same. Well, so let's consider what is the effect of this, of the load Q acting in the beam A on the node B. Okay, first of all, we draw the deformed shape. In the node B, it will be like this, because in the node A, sorry, in the beam A, it will be like this, because in the node A, we have the possibility to rotate. In the node B, we have that the rotation is prevented, because I am declaring it here. Similarly, no, apologies. Made a mistake. So the beam A and the beam B undergoing the load Q with these restraints will deform like this. The beam C obviously has no load applied, so has no reason to deform. Now let's consider this deformation means that some forces are applied on the beam. Since what is let's ask ourselves, what is the effect of the node B on the deformed shape of the beam A? Specifically, I'm talking about this point. Okay? We see that the beam would tend to deform like this, but the presence of this condition make the deformation like this. So we are applying a moment clockwise. Okay, do you agree? Or like this. In order to restore the horizontality of the beam in that node. So we can say that this is M. This is M, sorry, it is horrible. M applied on the beam A indicates 0. It means this is the effect of the node on the beam. So it means that the effect of the beam on the node, it will be opposed, equal and opposed. Do you agree? So it has to think that this node, what is the effect of this beam that deforms with this load on the node? Obviously, it will tend to have a rotation counterclockwise of the node, similarly to the one that you have seen with Professor Gentile during the first exercise, where only the load was present in the beam A, and so the rotation was counterclockwise. This was the effect of the load. Now let's focus on the beam B. We have a load on this other beam. The effect of the node B is similar to what we have seen before. So we have a moment that is transferred from the node to the beam. And this moment will be MB0. And obviously, the beam will transfer the same moment on the beam, but opposed. Then we also have some vertical load. Okay? Actually, we don't really care about it because we only have to impose, our aim is to impose equilibrium of rotation in the node B. So basically, we only want to know what are the moments that are applied on the node B induced by external load and by the rotation that is unknown. But if we also explicit the vertical reactions, the vertical forces, we can see that this method is helping us in solving also the structure. Okay, so we expect that the reaction of the node, so it means it's as if it is external reaction in the beam, in the node B. Sorry, I should draw it here. This is the shear force applied in the beam when the beam is undergoing this load. Okay? And if it is acting upward in the beam, obviously, on the node, it will be applied downwards. In fact, it is also the effect of the load on the beam, on the node. Okay? If we have this structure and we have an external load applied on the beam, what we expect is that the node will tend to be dragged downwards. Okay? Similarly to the node, to the beam A. About the beam C, we have nothing to say. So this is the case 0. Any question about this? I mean, at least something is clear.
Excuse me, I got lost for a minute. I didn't understand why we put the vertical forces.
We will see it later. Okay, it is not necessary to solve the displacement method, but it will come as in help for drawing the internal forces diagrams, because the superposition principle applies for everything. We have already seen it with the force method. So if we know the values of the internal forces that are acting on the beam for each load condition, then we can also immediately use the superposition principle also on these internal forces. And so we will obtain directly the diagrams of the internal forces. Okay, it's similarly to what we did with the force method. When we applied the force method, even if we didn't really need, sometimes we also explicited the reaction forces per each case. So when we apply only one static unknown, we can find the reactions for that case. Then we consider another case condition, another load condition, and we study the reactions also in the other load condition. And then we use the superposition principle in order to retain the actual one. Similarly, we are doing like this. The only thing that we need to know is the value of these moments and these shear forces. Well, we can use, you have already seen with Professor Gentile, the known cases. So we have a generic beam. So here we will use the stiffness coefficients, which are similar in principle to the flexibility coefficient. Okay. I want also here to explicit what are the flexibility coefficients on the beams and on the action. So if we consider a beam, a generic beam, with one section that is clamped in and the other section that is hinged. So here we have possibility to rotate at this in this node. And this beam is has a length L, has stiffness iota, and is undergoing a generic load Q, then we will have this bending moment, and we can call it M1, and it is equal to, obviously, not P, but Q. So it will be over 4. And then we also have T1, but we can also consider T2. T1 is equal, this is T1, I know that nobody would bet on it. A bit better. 5/8 QL, and T2 3/8 QL. Okay. Now we can see that the stiffness coefficients are the same in if they are applied on the beam or on the node, but obviously they are opposed in sign. Now, let's check the case number 2. So in the case number 2, we have Still have to explicit what is on the beam, what is. Here we have, oh no, before I said case number 0, now it will be case number 1, when we release the first kinematic unknown, that is phi equal to 1, okay? So if we impose a unitary rotation, we don't know the value, we just say that it is 1. First of all, we wonder what is the effect on the deformed shape of the beams. Obviously, this node will have rotation. So it will be okay. Like this, then like this, and then like this, okay? Because we have possibility to rotate at all the 3 ends of the beams. So it means that we are applying these moments on the beam, okay? So clockwise moments that induce clockwise rotation at the beginning of the ends of the beams. So we can call this M1C, because it is the moment applied in correspondence of the kinematic unknown 1, that is the only unknown we have, in the beam C. M1B, M1A. Okay? We do not only have these moments, we can also, I don't know, okay, first of all, we draw the effect. And obviously, when we impose a kinematic quantity on one node, we expect that all the reaction of the system is opposed to this to this imposed displacement. Okay? I do not draw again what is what, because it's trivial. But I want to explicit also the this should be first. Just give me 1 second. And we can find all these coefficients in the diagrams. This is downward, this is upward, and this is in this direction. These are opposed. Obviously, this is T1A, T1B, T1C. T stands for shear, in Italian taglio. Okay, so the capital T stands for taglio. And now, we want to know the values of this displacement, of these forces, sorry. The case we have to refer to is this one. So we have one imposed rotation at the beginning of a beam, the other end of the beam allows for rotation. So the deformed shape will be like this. I wanted to explicit what's on the structure and what's on the node, so that if it is clear once, it is clear for all. M1. But we also have T1, and here it is opposed. T2. And we have apologies. M1, T1, and T2 in this case. Well, T1 is, no, sorry, M1 is 3 over iota over L times iota over L, and T1 is equal to T2 for the vertical equilibrium of the beam, and it is 3 iota over L to the power of 2. Can you see what I'm drawing? I mean, maybe it's not so straightforward. Okay, so far so good. Can I go on? Yes, no, maybe? I mean, there is something you are not getting, or it is everything that you're not getting? Okay, since I have no feedback, I will go on. We are applying the superposition. So I am assuming that everything is clear, and for example, and for the exam, everything will be perfect. This is node B. So we just collect all the information we found here. So these are the moments that are applied on the node B in the case 0, and these are the moments that are applied on the node B in the case 1. So in the case 0, we had only these two that were M B0, M A0. This is the A. Okay. Then three moments that are the same, basically, because the geometry is the same for all the three beams, are M1B times the rotation, which is unknown. M1B times the rotation, which is unknown, and obviously it is not B, but it is C. M1A times the rotation that is unknown. We impose the equilibrium to the rotation in the node B, and what we get is M0A. No, okay, first of all, we have to impose some reference. So let's say that all the clockwise rotation moments are positive. So we have M0A, which is counterclockwise, minus, plus M0B, B0. That is positive because it is clockwise direction. Then all the other three moments are negative, minus P that multiplies 3 iota over L, or L to the power. Check. No, okay, L plus the same for the beam B plus the same for the beam C. All this stuff is equal to 0. We have one equation, one unknown, and we can find its value. But M A0 and A and B0 are the same because they were both QL power to the 2 over 8. And so we have that these two terms get 0 minus phi multiplying 9 iota over L equal to 0. Obviously, this means phi is equal to 0. Okay? Because we have phi multiplying something equal to 0. So it means that our structure has no rotation. Well, this is no surprise because the structure was symmetric. Okay? Now we have to solve the structure. And how we do so? We solve the structure. Well, we have the three beams with the reaction, with the strains, sorry. We also have the load applied, acting only on the beam A and B. Now I am just splitting it in order to make it more clear. Okay. We have also these reactions that are brought from the node to the beams. So that we have that this and this are applied on the beams. Okay. So we have this was 5 over 8 QL. This was 5 over 8 QL. And then we had the moment negative in both beams, whose value was QL to the power of 2 over 8. Okay. We also knew, if we want, that the reaction at the opposite node is 3 over 8 QL, 3 over 8 QL. How do we know that? That's easy. If we go here, no, not this, sorry, wrong page. Here we go. If we consider the generic case that we adopted in order to find our stiffness coefficient, we had the bending moment and the shear force in both nodes. So we also add T2, this one, that is basically the vertical reaction in this beam associated to the load applied Q. Okay? So that's why I also took the shear forces from the stiffness coefficient, not only the bending moment, because in order to find the value of the unknown rotation phi, we needed the bending moment. But if we can solve each load case, and we can also find the static unknowns at both ends, meaning the reactions for each load case, it is very helpful for us, because now we don't need anything else. We don't need anything else to solve the structure, because we already have everything. What we need now is find the value of the shear force. This is our reference, as usual. But it is very straightforward. This is our structure, very ugly. We have that in the node A, apologies for this up and down and everything. In the node A, we have a vertical force 3/8 QL. So it is positive with our reference, this one. So we have shear force. Come on. We have that shear force is positive 3/8 QL. It is positive. In the node B, belonging to the beam A, we have this shear force. Okay. So it is opposed to our reference here. So it is negative. Okay. Apologies. It is negative minus 5/8 QL. On this other part, the beam, we have 5/8 QL positive. And here we have 3/8 QL negative. Obviously, on this beam, we have no shear force. Now, shear force, axial force. Okay. Obviously, we have no shear force in the beam A and B, but we can easily understand that these two shear force, this one and this one, applied on the beam, are applied on the node. Okay, so the node transfers also these two forces to the other beam. So here we have 5/4 QL, because it is the sum of the first two ones. And it is easy to find. I will explicit it in the new page. Okay, we had 5/8 upward, 5/8 upward. It means that on the node, it is 5/8 downward. What's happening? I don't know. It means that what is the force that is exchanged between the beam B and the node B and the beam C? They exchange some unknown force, and if we make a vertical reaction in the node B, we can find that this is obviously minus 5/4 QL, because they are everything QL. it means that also this is minus 5 over 4 QL. So it is compression negative 5 over 4. This is 4 QL. Okay. Then obviously we have to ask ourselves every time we cut the structure everywhere, what are the three forces that each part of the structure is exchanging with the other one. Okay? In this case, there was also this force. Then finally, we consider the beam, the bending moment. That's obviously because we can solve it, but it is very easy to find that it is this drawing 2L to the power of 2 over 8. In order to find the actual value, we have to impose the equation as usual, but that's trivial, and this is the result. Okay? No bending moment on the beam C. Now, if everything is clear with this exercise, we can go on and start a new one. If there are any doubts, this is the moment. I'm starting to. Drawing the new one. This is more complex. All the dimensions are once again L. We have node A, B, C, node A, node D, beam A, beam B, and beam C. Only one load is applied. On the beam A. Okay, we want to apply again the displacement method. First of all, we have to ask what are the static, sorry, the kinematic displacement we want to explicit. Well, in the beam, in the node A, we have everything fixed. In the node D, everything is fixed as well. The node B, we want to know, can the node B undergo an horizontal displacement? Yes, no? Someone wants to guess? Is someone alive? Hello?
I think B cannot have any displacement because also A and C can't have displacement. So.
Okay. Yes, that's right. The node B cannot undergo any horizontal displacement because we said before that we impose axial stiffness of all the beams. So if the beam AB is axially stiff, and if at least one node, in this case the node A, belonging to the beam, cannot undergo horizontal displacement, and the node A cannot, because it is clamped in, it means that no point of this beam can have horizontal displacement. Okay, so we do not need to investigate the effect of horizontal displacement in the node B. What about vertical displacement? Any guess? Can it have a vertical displacement, the node B, or not?
No, because it's the same situation as before.
No, actually no. That was a trick, but thank you for answering. Actually, if you think that the beam B is actually stiff, and so it means that it cannot undergo any vertical displacement, well, this is not true, because no point in the beam B is vertically constrained. I mean, the node B can go upward or downwards, because the beam A can deflect. Okay? Similarly, the node B. Oh no, that was the rubber. Okay. Similarly, this node, this beam C, can deflect in one way or the other. So it means that the node C, in principle, can go upward or downward. So it means that the beam B, I mean, this is try to think about one structure like this. Okay. It can be also some chair, some weird chair. We can easily imagine how it deforms when this load is applied. I imagine that it will tend to go downwards. This beam will go like this, because come on, I have to draw again. I mean, the beam A will tend to deflect downward. The node has to have the same rotation between beam A and B of 90 degrees. So it will be something like this. The node C can go downward, but cannot go right or left, because the beam C is actually rigid. And this doing? Come on, vabbè. Okay, it's not the best drawing I ever did, but it is clear that we can have something like this. Okay, so we can expect some displacement, and we will call eta, and some rotation, and it will be phi. Now, new page. Let's consider what are the effects of the unknown eta, of the unknown phi, and of the external load on the node B. And then we will have to impose the equilibrium of rotation and the equilibrium of displacement, vertical displacement, in the node B, in order to find the true values of the displacements. I mean, can you understand why this method is more powerful than the force method? In this case, we have two beams, and 1, 2, 3, 4, 5, 6 7, 8 degrees of redundancy. Okay, in this case, it is the same. We need to write two equilibrium equations with the displacement method. And with the force method, we would need two compatibility equations. So it is the same, basically. But in case we have a structure that is highly redundant, with the displacement method, we don't need to write one equation per each degree of redundancy, but only for each node that is on the structure and can undergo an unknown displacement. So, superposition principle, case 0. Okay? Sorry. Case 0. So we study the effect of Q, but we impose that the rotation is equal to 0 and eta, the displacement, is equal to 0. So we are fixing that point. Times something. Okay. Okay. I wanted to use red color for the loads. We have this. We have to understand how this beam will deflect. And obviously it will be something like that. Now, the reactions on the beam induced by the nodes, obviously, it will be some bending moment, M0A, and also the vertical reaction, TA0. Why it's not drawing anything? Okay. So on the node, they are applied equal but opposed. On the other beam, there is nothing happening. Okay, because we have no load applied on the beam B and C. We go on the tables and we see that M0A is equal to Q, L to the power of 2 over 12. These are very important numbers and you should really try to remember them. Again, the shear T0A, similarly as before, is QL over 2. No, before it was different because the structure was not symmetric. But in this case, the structure is symmetric because the beam is clamped in both in this end and both in this end. And so the load is similarly applied on the right-hand side and on the left-hand side. So that's it for the case 0. Now, new page for the case 1. We have to consider the influence of the displacement, eta. It never wants to draw the beam C. So imagine that the beam, the node B is undergoing a fixed eta equal to 1. Okay? It means that the deflection, here it will be something like that. We have 0 rotation at both ends. It's really bad at drawing. Apologies. Then this node is going downward. The deflection of the other part of the structure will be something like this. Okay? The beam B just translates downwards, and the beam C deflects. So the effect on the beam of this displacement obviously is a downward shear force, T1, because it is case 1 belonging to beam A. And it's also like this. And then there is also this effect, M1A. M1A, T A1. Now the beam B actually does not transfer anything, but the beam C does, because there is this beam is something like a clamped-in section and a hinged section with a unitary displacement at the hinged one. So if we go, so it is similar to this. I don't know what it does sometimes. What is it? Come on. Okay. Come on now. Okay. This is the case, and so we know the shear force that is applied on the beam, and so the reaction of the beam, which is 3 iota over L. Now I'm drawing it better, L to the power of 2, apologies. So we have T1, and the values of the unknown are M1A, and it is equal to 6 iota over L to the power of 2, I would say. T1A, that is 12 iota L to the power of 3. T1C is equal to 3. We did it before. Yep. 3 iota over L to the power of 3. That was a mistake I did before. The exponent is 3. Okay. These are the coefficients for this case. Now, new page, and let's see the last case. Oh, what am I doing? This was the previous example.
Can you go back for a second to the last exercise?
Sorry, can you repeat?
Can you go back to the last exercise a bit, please?
Oh, sorry, apologies because I have a terrible echo, so please try again now. or write it in the chat. Of the last exercise. Yes, can I do it after a while? So now let's just focus on this. Then I will go back. And if I forget it, please remind me. Okay. Okay, yes, this is the case 2, where we have no load applied, unitary rotation, and no displacement. So this node is just rotating. We have just seen it. Usual. Deformed shape will be something like that. Something like that. Okay. We have M2 belonging to B A. Here force BA2, and so they are opposed on the node. Again, MB2 E2. I think it is right. Yes. The values of M2A is 4 iota over L, because it is this case, M2B is 3 iota over L, as we already saw before. A2 is equal to 6 iota over L. Okay. So now we can simply impose the equilibrium equations. Okay, I'm trying to be fair with those of you. Prefer I write in capital letters. Equilibrium equations. The first
Excuse
one.
me. Could you go
Yes,
back
sir.
to the last page for 1 second?
Yeah, sure.
Thank you. Okay, thank you.
Okay, no problem. Sorry, I just shifted page without asking if I could. My bad. So the first equilibrium equation is obviously related to the first kinematic unknown that we have addressed. So Fy is equal to 0, because it was related to the vertical displacement. We have to go back. In the case 0, we have the shear force, that is T0A. So we write T0A. Okay. First of all, we fix the positive downwards. Okay. So it is positive on the node. Here, what do we have on the node? It is upward, and it is T1A. So minus T1A times eta. Because T1A is the force associated to a unitary displacement, but the displacement, actual one, is unknown. Then, case 2, here we have, again, downward T2A times P, and it is equal to 0. Okay? Let's see if this. There is something else I'm forgetting. Yep. Here. I'm forgetting because I forgot to transfer it here. Okay, actually, if we look at this, this was downwards because this was the effect on the beam. Okay, T1C is downward because it is pushing downward the beam. It means that the reaction here, it will be upward because it is the reaction of the beam, TC1. So here, we have two terms for displacement, T1A and T1C. The second equation is the rotation in the node B, obviously. And so we have the MA0 that is counterclockwise. Let's consider counterclockwise positive. Okay. We just set a reference and then we behave coherently. So it was counterclockwise, so positive M0A. Then the effect of theta equal to 1 is a clockwise moment MA1, this one. So minus MA1. I'm not drawing anything because times eta, which we don't know. Then the second case, we have Q contribution. Both of them are counterclockwise, so positive, and they are MA2 and B2. B2. Both of them multiplying the unknown P. Okay, so far so good. I mean, nothing too much special. Now, I would like to just substitute the terms, and then the resolution is quite trivial. I will show you with a couple of slides. So T0A this is downward, it's right. Ah, okay. I forgot something. Do you notice any mistake here? specifically here. These forces, I consider them positive. Okay, it was right before, then I wrote it again, and I made the mistake. But you can notice that I put all these forces positive, but my reference was positive downwards. Okay? And if we go back here, when we were studying the case 1, we can appreciate how both forces are going upward in the node. Okay? So this is wrong, and this is minus. Okay, cool. So equation 1 becomes P, no, Q. L over 2 minus T1A and T1C is 12 and 3. Times eta, that is unknown, plus T2A is 6 iota over L to the power of 2. Yes, multiply times theta, theta. Then, second equation, we have M0A, which is 2 L to the power of 2, over 12. Okay. Minus MA1 was 6 iota over L to the power of 2, I think, plus these two terms, which are respectively 4 iota over L and 3 iota over L iota. Equal to 0. So it means that we can draw it as and minus iota over L to the power of 2 L theta. Don't worry, because you will find the slides with everything. And now I'm showing actually slides. This is the final problem, which leads to this solution. Now I'm as soon as the slides down. Okay. This is the same exercise as you will find in the slides. And here you can see the resolution is already proposed with the value of phi and the value of eta, which guarantee the equilibrium in the node B. As we did before, it is nothing new. We just explicit the effects using the superposition principle, so considering both the loads, the bending moments, and the shear force of case 0, plus those of case 1 plus those of case 2, each of them multiplied times the actual value of phi and theta. And we can find these reactions. Once we know the reactions, it is trivial to find the distribution of internal forces, because the structure actually is very simple. Okay, it is just cantilever, nothing else. And this, most important, is the deflection of the beam. And as you can see, it is basically the same that I drew before with the inflection, with the deflection of the beam A and C, and the small rotation of the beam B. So far, so good. Now, okay, before switching to the last case, Andrea asked me if I could go back to the results of the first exercise, and it was, I think, this one. Yep. Is there something specifically you want to see?
No, I just need to copy something.
Sorry, could you please pick up? Could you please repeat? Ah, okay, okay. No, but everything is already in the slides, so you will be able to see the results as soon as the slides are delivered. But apologies, I know I just went too quick. So now I would just close the displacement method. Just the last 10 minutes, I would like to devote them to some consideration about the case that we started to see last week. And it was the continuous beam over 4 spans. We saw the hand resolution of the problem just by hand. And then we saw how we could use Excel in a smart way in order to find the same results. And then we verified those results that we obtained by hand computation and with the matricial resolution with Excel. And we verified those results with Telaio 2D. Okay? But I also want to show something else. As soon as I find it. Because Excel is quite interesting, because we can also exploit it in order to find the resolution when the structure is not symmetric. And when the structure is not symmetric, we know for sure that the resolution is not that trivial. We exploited the symmetry during the last exercise in order to remove one unknown, because the problem is actually 3 times redundant. So we have 3 unknowns. Let me share this. Okay. So the problem was 3 times redundant. We just exploited symmetry to remove 1 degree of redundancy. But when there is no symmetry, the problem is more complex. and is more and more complex as the number of redundancies increase. But we saw last time that the resolution with Excel and also by hand computation, if we want to use the matricial consideration, only requires for a matrix of coefficients, that is this one, and a vector of known terms. This vector depends on the external loads. We have already seen this. So using Excel, we can just solve the problem and find the values of x1, x2, x3. But as long as we consider a structure with more spans, we can, in the design phase, consider that different load conditions induce the greater, so the maximum or the minimum bending moment or reactions at different points. And we will see now a small exercise, small case. If we consider just load, okay. These are the coefficients that we need to take into account for the matrix when we load the first column, the first beam, and we do not load the columns, the beams number 2, 3, and 4. You can see that using these are just the coefficients effects, and it is very easy to compute them because their equation is always the same. Everything that changes is only the load that we have to take into account or the length of the beam. Combining these terms, when we want to load with Q1 or Q2, and I will recall you, Q1 was when we were just loading the smallest possible, whereas Q2 is much higher than Q1. So we consider a high load on the structure. So if we want to load a lot the first beam, we can consider one case or the other case. When we load with just Q1, we will obtain this value of the coefficient. Whereas if we use the higher load, Q2, we will have a different PC. PC is just the rotation, delta rotation in the node C. So we can consider different cases when we want to load each beam with a load Q1, Q2, Q1, Q1, for example. So we want to maximize the load only on the second beam. But we can also consider when we load the maximum on the two central loads, on the two central beams, as we did in the first exercise, with the lateral spans with load Q1 and the other ones with the central ones with Q2. In this case, we will need to take this term loading with Q1, and this term loading with Q1. The central ones are with Q2. Again, we can solve the structure. We can find these terms, just summing up different coefficients associated to different load conditions. So when we load the N1 and 2 with Q2, whereas the other two spans are loaded with Q1. So what changes, as a matter of fact, from the previous exercise is only this vector. And this is very easy to understand, because if I load in a different way, only the flexibility coefficients associated to this external condition will change, whereas the matrix coefficient of the unknowns, of the static unknowns, is always the same. So we can just reply the equation that we adopted in order to find the static unknowns, which hold for the coefficient of flexibility coefficient and the known vector. We use the same formula and the same matrix here, but calling every time for a different vector associated to a different load condition of the structure. And so we will find these three static unknowns, x1, x2, and x3, that are immediately available. And we can find that if we load differently the structure, we will find different values of static unknowns. What is most interesting is if we want to consider the minimum bending moment ever associated in the structure in the node E, okay, so it would be x2, we can find that the minimum possible bending moment is found when we load only the two adjacent columns, the beams. So if we want to maximize the bending moment, the negative bending moment in correspondence on one support, we have to load at maximum the two adjacent spans, whereas all the other spans have to be not loaded. In this case, we have to consider the minimum load Q1. And varying the load conditions, we can have also higher values of static unknowns in the first and the last internal span. Similarly, we will find different values of the maximum bending moment in the span. Okay, so for example, just to verify it, we can use TLIO2D. We already saw last time it is a matter of 2 minutes to define the structure if TLIO2D starts. Okay, it's not starting. I don't know what's happening, but TLIO2D won't start, and if it doesn't start, you just have to trust me. Okay, now it's starting, and it will start for 10 times. Okay, now I'm just sharing the right window. So the geometry was 15, 10, right? Yeah. So we create the new structure. Create node. The first node is here. Then 10 meters. At 15 meters. 5, 40, and 50. It's nothing new. We already did everything last time. we connect each couple of nodes. We impose the restraints, so hinge section, the beginning and the vertical supports, all the other external ends. Then the load, if we want to verify the loads are distributed loads, so let's just resume what we did last time. And then impose the material properties. Okay, finally we get it. We select not that one. $500, just to avoid any problem. And we can solve the structure. My laptop is going very slow this morning. I don't know why it is taking so long. We can change it. Maybe HPA. This is a problem that can occur when we have too large deflections, and the software just tells us. In this case, we'll just increase. We just increase the cross section inertia, so we can find the results. Okay. Sorry. Just subdivide all the beams in two so that we can find. Okay, now we can resume the number, the unknowns. So it was 227.9 as negative moments and 444.8.5 was this one. And the maximum bending moment associated in the central spans were 224 in these two beams. But is it the worst case we can expect for the bending moment in the second beam? Because when we design, we have to foresee the worst case scenario. So let's remember 224. If we just change the load condition, so distribute the load, this and this will be now -5. And we can also increase the load here. and we solve it again, we can see that for a completely different load combination, we can find that we will find 292 kilonewton meters kilonewton meters bending moment in the second span. That is way bigger than what we found before. So we need to consider the right combination of the loads in order to find the maximum internal forces that I can expect. This is very important when we design the structure, as you can imagine. So the lecture for now is done. I hope that everything is clear. And as usual, if you have any question, please send me an email and we can discuss about it. If you have any question right now, even if we don't have time because it is going to start the next lecture. So I wish you a very nice evening, weekend. Sorry, someone asked something?
Yes, hello, Professor. I'm Maria. I had a question actually. I
Yeah.
saw already on Service Online that there are the dates for the exam available. And I wanted to ask you if you can give us feedback, more clear feedback on how the exam maybe will be structured. Like, I don't know, maybe the exercises or even the programs we will have to present and stuff like that. Thank you.
Yes. So this is very simple, but I encourage you to ask Professor Gentile, who will discuss about it. The exam is obviously an oral exam because the resolution of the exercise will be evaluated with the homeworks. So that's all. You will be asked during an oral exam just the topics that are discussed in class by me and by Professor Gentile about the methodological viewpoint and the theoretical background of the content of the homework of the course. Okay.
Yes.
But about the exam, ask the professor.
Yes, I will ask him next week already.
Okay. So have a very good evening and weekend. Sorry, not evening.
Thank you.
You too. Thank you for the lecture.
Now, if Professor Gentile is already in, I can restore him as.
Yes, I am here.
Okay, now I am giving you back all the superpowers.
Okay, but I will wait more or less 1 quarter before beginning the next lecture.